I don't know, some of you know this already, but we have a very special event today. Not only is it Memorial Day, but one of our own has a birthday. Does anybody know who it is? No. Dale, come up here. Don't sit down. Should we wait till dessert or should we do it now? Let's do it now. And you have to sing too. Right in the microphone. Oh. On three. 1, 2, 3. Happy birthday to me. Happy birthday to me. Happy birthday, dear me. You. Happy birthday to me. Okay, let's have some food now. Thank you. Good afternoon, everyone. Can I get your attention? This conference wouldn't have been possible without help from a lot of special people. We've got some amazing volunteers that really carried through. Nate is my co-chair. Did all of you know that? Well, you do now. Thank you. And Miles has been here every step of the way. He's been a phenomenal volunteer. Thank you, Miles. Tanisha, come up here. Come on. Yeah. I already gave you one of these, so you don't get another one. I'll watch. We call them the award. We call them pointy things.
It's a pointy thing. All right. Thank you, Dave.
You're welcome. Here you go, Tanisha. You're welcome. I have to give you a hug. Okay, let's get lined up here now. Come on, come on. That lettuce in my teeth? I feel it. Hey, who knows who Steve McQueen is?
Not me. He says I look like him. I don't know who he's talking about.
Yeah, pull it.
I'll Google that now that I have time.
Yeah, now you'll see. All right, Luisa, are you ready for showtime? And another leader extraordinaire in many areas, education, volunteers, you name it. I'm so looking forward to what she's about to do. And do you want to make an announcement about that?
No.
I didn't think so. I wouldn't either.
Not yet, not yet.
Okay.
Good.
Well,
We ready?
it's showtime for you. Thank you very. Oh wait,
Yes.
Bob, you want to come up?
So this one I will announce. So Bob, on behalf of the National Space Society and the National Space Society Puerto Rico chapter, we want to thank you for sponsoring our Arecibo Observatory students to participate in this program. It's the first time Puerto Rico's come to ISDC as a delegation, and it's thanks to the support of the Arecibo Observatory and NSF. So thank you, Bob.
Stay or go?
No, you can stay. I'm just going to introduce Dr. Robert Kerr, a.k.a. Bob. Dr. Kerr is the director of the Arecibo Observatory. He holds a bachelor's in physics from Ohio University, Athens, a master's in atmospheric physics from Michigan State University. University of Michigan. I was meant to confuse him, I know. And his PhD from there as well in 1986. He worked in the Aerospace Corporation in El Segundo for 9 years, and from Segundo, California, and then he was professor at Boston University for 9 years. He formed his own company called Scientific Solutions Inc., where he's co-owner, and they focus on the development of optical instrumentation for space instruments, especially Fabry-Perot cavities. He worked as an NSF project manager, and he's been the Arecibo Observatory director for 4 years. He loves fly fishing, I have to say that. And he was drafted to be a pitcher for the Orioles when he was younger, so we got a baseball fan. His favorite movie is Apocalypse Now and Oz. And it's always a pleasure to work with you. And thank you for letting us use the pool at the observatory to prove that you can play Quidditch in space and calculate the equations of motions for my students and their Quidditch game. So thank you, Bob.
Thank you, Luisa. That's more information than you needed, I think. I'm not a great public speaker after all of that, but in fact, I see a mistake on my first slide. I got the wrong year, so it's not a good start. But anyway, thanks for the invitation. Thanks for letting me speak and letting me be here. This is kind of the first time, I think, that Arecibo Observatory has formally been involved with the ISDC or the NSS and this group in general. And I think we would very much like to be an important part of your future. So hopefully that's my overarching point here. And what I'm going to talk about is perhaps more of the history of the observatory and what we do now, because I'm not sure how much folks are aware of that, than I am about our educational programs. But in the end, what I want to stress is the educational programs, and I hope I'll move quickly to that part of the talk and describe to you what we're involved in now in terms of education, which I think is essential to the future of the observatory. Many of you are probably aware that the observatory was threatened with closure 5 years ago when I was first director for Cornell. I think we've turned that page, and we're pretty solid for the next 2 generations. But a big component of that is our public outreach and our education programs, and I want to describe that. I will welcome you to, I do better if you interrupt me while I speak and we can interact, and if you have questions, I would be happy to field those as we go along. Okay? Thank you. We renamed the telescope, by the way, some of you will be interested in this, to the William E. Gordon Telescope, and he's the true genius behind Arecibo Observatory. He conceived the observatory when he was a graduate student at Cornell in the 1950s. He actually almost single-handedly came up with the design of the telescope. The idea of the telescope was actually not as an astronomical instrument, but as an instrument to measure the ionosphere. And the technique we use to do that is a technique called incoherent scatter radar observations. And he was a pioneer of the theory of incoherent scatter radar and calculated we'd need a telescope about 1,000 meters in diameter in order to receive the backscattered signal of radio waves from the ionosphere. It turns out, very fortunately, he was wrong by a factor of 10. And so the telescope is literally 10 times larger than it needed to be to do the experiment it was designed for, and that's why historically it became an instrument for astronomy. Okay, so this is our 50th anniversary year. We became operational in 1963. It is still the largest single-dish telescope in the world, and we do atmosphere, which I will stress in a subsequent slide in 3 different areas that I will get to in a minute. So I'll start out with our accomplishments. This is a picture of the main part of the focus platform, what we call the triangle, being lifted into place in 1962. The telescope, of course, has a very simple design. It's a steel bridge suspended over 3 towers. It's different from our normal steel bridge only in that the suspension cables don't have that graceful sway you normally see in a steel bridge. They're pulled tight so we can maintain a focus. In fact, the legend is if the suspension cables should become 45 degrees in temperature, they'll snap. So they're held very firmly in place. And in that way, it's different from a steel bridge. The other difference is this bridge is in motion, and we maintain that motion to better than 1 millimeter. Real quickly, as I said, the telescope was conceived by Bill Gordon. It was originally the Arecibo Ionospheric Observatory. It didn't do astronomy, and the total cost was about $9 million. The potential for it to do radio astronomy was realized by a gentleman named Tommy Gold at Cornell University, and Cornell operated the observatory from its inception until September of 2011, and on October 1st, 2011, new management is now SRI International of Menlo Park, California, in partnership with University Space Research Association out of Maryland and Universidad Metropolitana. So for the first time in the history of the observatory, in fact, the organization that takes most of the money from the cooperative agreement with the NSF is a Puerto Rican institution, Universidad Metropolitana. Oh, this is a picture here on the upper right, if you can see it, of the original sinkhole where the observatory is located. It was originally a tobacco farm. And there you see the triangle after excavation of the sinkhole, which was minimal, ready for raising, again in 1962. So why is this great observatory in Puerto Rico? Well, nearly all the great astronomy observatories, of course, are located near the equator, where you can see the entire sky. You rotate beneath the entire sky during the year, whereas at the poles you only see half the sky. And the karst topography of this region in Puerto Rico is rather rare geological landform worldwide, but has a series of sinkholes that made excavation for the telescope location very simple and minimal. Also, that same karst terrain provides a natural protection from radio frequency interference. So that was an asset. And of course, the observatory resides directly below the ecliptic plane, allowing us to observe all the planets during the year as well. So here's an aerial picture of the karst topography. I've been talking to some people. I want to build a second one of these dishes, actually. And you can see other candidates in the nearby area potentially to build a second Arecibo. But you can see the natural positioning of the spherical dish in the karst topography. These are our control buildings nestled in the karst down from the telescope. That includes a control room that's in the forefront here, where we have a computer department, electronics department, and our scientific office space is then in that building in the back. And a library, which we're getting rid of. We'll talk. Okay, so just a couple of quick pictures. Here's the beginning of the excavation of the sinkhole. And here's actually the finished product. Well, very simple idea. The original telescope surface itself was nothing but a chicken wire, about 1 square centimeter density of that wire, so you could see through it. And that was the original dish as it was inaugurated in November 1963. So the entire dish is 1,000 feet, 305 meters across in diameter. From the bottom of the dish, it's spherical, to the edges is about 160 feet, and then 435 feet above it hangs the focal plane. And it hangs from a curved azimuth arm that's about 300 feet wide, and that azimuth arm spins on a railroad tie, a railroad rail that is at the bottom of the triangle, so we can look in azimuth. And it also then, the receivers ride up and down on the curved azimuth arm, so we can look as much as plus or 20 degrees off of zenith. So that's how we point around the sky, which, if you're familiar, by the way, with the FAST telescope, is not how the Chinese are going to do it. FAST telescope is a bigger telescope that the Chinese are building and should be done in 2016. So this is the original instrument, the console. You can see the post-war technology. It's a 430 megahertz transmitter. It has 2 megawatts of power. So it's about 4 times more powerful than the most powerful commercial radio stations in the US. Because we get 70 dB of gain from the antenna, we actually can transmit isotropically about 140 terawatts of power. This was the original receiver. Because it's a spherical dish, the energy focuses into a line. So you put a series of long antennas to gather the reflected energy from the dish. This is the first of those antennas at 430 megahertz. It's about 100 feet long, about 95 feet long. If you visit the observatory today, you can see this antenna on display at the visitor center. Okay, and this is something I want to stress, and I think it's relevant to this community as much as any. There's no other observatory in the world that is as broad, has the breadth of research that Arecibo Observatory does. We do radio astronomy, planetary radio science, and atmospheric science. Those are our specialties. Unlike almost every other telescope in the world, we transmit. Okay, Goldstone also transmits, but we transmit at 430 megahertz, as I just said. We also transmit at the S-band at 2830 megahertz for our studies of near-Earth objects and planetary surfaces. So actually, Arecibo Observatory has been and remains on the cutting edge of 4 really important areas of research relative to human sustenance on this planet: gamma ray bursts, asteroid or comet impact, space weather, and global climate change are features of the research programs that go on at Arecibo Observatory today. Pretty wordy. I'll go through this really quick. We are 50 years old. but the instrumentation at the observatory is not. The surface was reconstructed. I'll show you a couple pictures of that in 1973. Passive optical instruments, which is actually my bag, were added as early as 1965. We added the transmitter that I just mentioned in 1973. We also have some of the highest power lasers in the world, or LiDARs, for probing the middle atmosphere of Earth. Those were added in 1995. We made a, yes? We do Rayleigh lasers in green line, so those are roughly 5,500 angstroms. We have resonance LiDARs that resonate at sodium and at potassium, so 5890 angstroms and 7320, I believe. And so the most powerful laser we have approaches 10 watts. But there are new fiber lasers that are going to take us to 50 watts. Where was I? Lasers, okay. No, yeah, in 1997, I mentioned that the surface focuses the energy to a line. We added a Gregorian optical system that converts that line to a point. And so we basically, as I'll show you in a minute, added a giant golf ball with 2 additional reflectors in it, a secondary and a tertiary reflector that converts the energy to a point. And that allows us then at the focal plane to just have a rotary floor that rotates receivers into place depending on which frequency you want to hit. Before that, we had to actually drop the old antenna and bring up a new antenna for any frequency change we want to do. So that was a major upgrade. We also added a more powerful, well, we also added a ground screen to protect us from RFI and to lessen the noise on the signal we were after. We added an S-band transmitter in 1997 that is as powerful as 1 megawatt before you add the gain of the antenna. We added a visitor center, which is really essential to our future from my point of view. In 1997, it's a center of educational and public outreach activities. We added a 7-pixel radio camera in 2004. It's allowed us to survey the region of the sky we can see in a matter of years at all different frequencies. Okay. Oh, yes, and right now, which I'll get to, I don't know how long, I'm going to go over time for sure. You got to cut me off when it's time to cut off. We currently have a project which is a high-frequency transmitters, which are basically old transmitters that we got for free from the Air Force from the over-the-horizon radar and the DEW line system that we're going to use to actually interact directly with the ionosphere, transmit radio energy to the ionosphere, move electrons at very high velocity, cause them to recombine, and basically make the ionosphere over Arecibo a giant plasma laboratory. So here's a picture of the resurfacing project in 1973. We put on about 39,000 aluminum panels that allows now the telescope can reflect and be used all the way to 10 gigahertz. This is the way it looks under the dish. Most people think from watching the Bond movies that it sits on the ground. It does not. Again, it's a beautifully simple system. It's a cement wall that surrounds a sinkhole where large cables are hung from one side of the sinkhole to the other. And so those cables naturally form a catenary shape, which are then pulled into a perfectly spherical shape by subsequent cables pulling on those. And the aluminum panels are just set on that cable system. Okay? So this is the way it looks under the dish. Everything about Arecibo is big. It costs us about $50,000 every year to keep these weeds from growing up through the primary dish. So Louisa suggested that we use pygmy goats, which we're going to try. On the other hand, you can't denude it altogether or else the thing erodes and the whole thing collapses, so it's a balance.
I'll see you later about packaging the residue from the goats and selling it. Yeah.
This is an excellent idea. I think it's something we need to do. Somebody else asked about growing crops under here. In the 60s, I understand there was a cash crop grown down here, but we haven't. I had nothing to do with that. Okay, I'm going to go a little quicker because I think I'm going to run over time. I mentioned all these things, basically the upgrade in 1997 that allows us to gather the energy at a point. This is a drawing of the Gregorian dome. It's a giant golf ball, and you can see basically the ray trace of the energy first hits the upper part of the dome, which is the secondary mirror, then onto a tertiary, and then onto the rotary floor. I should have asked for a pointer probably where the receivers spin around. But this is the general idea of the Gregorian. So this is the way the telescope looks today. You can see the Gregorian hanging nearest you, and on the far side remains the 430 antenna from which we both transmit and receive. And there's a second 430 transmitter inside the dome. So we are the only incoherent scatter radar in the world that actually has two beams that allows us to look around the sky. And then you can see the azimuth arm now very clearly and how that mechanism allows us to point around the sky. The downsides of Arecibo, for those who are interested, is that we don't move real fast. We're a little bit of an elephant. So actually searching for asteroids is not our bag. Once they've been identified by the optical people where to look, then we're really good at getting the orbit exactly or even getting images of the asteroid, but we don't really find them. The other thing is, we believe it or not, we can't see the galactic center, which is a real problem for our radio astronomy program. And both of these issues are reasons why I'm interested in building a second Arecibo. This is a cartoon, really, of the rotary floor, and you see all the different receivers that we currently have in place. Basically, again, we go from 430 megahertz all the way to the X-band at 10 gigahertz. This is just a picture of the ground screen now, around which is a track, the so-called rim road, which our staff uses for exercise. This is, again, a list of the frequencies that we do, but I won't bore you with this. I guess this talk will be available to folks afterward or somewhere, somehow. Whoops. This is the Alpha camera, which we're very proud of. It's a 7-pixel radio camera, which is pretty novel. It was added in 2004. It makes us by far the most sensitive radio telescope in the world. Has basically 14 beams when you count both polarities. And these images that I show here, you can kind of get an idea of the size of the thing and the size of the operation. This is being a very industrial site. You can see it being lifted in place there on the lower left with a guy hanging out 400 feet above the surface, you know, participating. So it's a very dangerous site. And here's a picture of the Alpha camera proper. This guy's actually only about 3.5 feet tall. All right, a little bit of the science that we've done. Some of you are familiar and some of you are not. We did receive a Nobel Prize for work that was done in 1974 by Russell Hulse and Joe Taylor, wherein they discovered a binary pulsar system that allowed them to time the decay of the orbit of that binary system. And that timing, of course, confirmed Einstein's general theory of relativity. And for that work, they received a Nobel Prize in 1993. Arecibo has essentially mapped the structure of the universe, the nearby universe, in terms of galactic structure. And to make a very long story short, it turns out that structure is not isotropic at all, as you might expect from basic cosmology and our current understanding of the Big Bang, but actually has a lot of structure to it. And that structure remains a real challenge for the detail of cosmology henceforth. We participate now, you know, when you have one big dish, the problem you have is you don't have great spatial resolution. Right? The farther your eyes are apart, the better spatial resolution you have. So we also participate now in the very long baseline interferometry system. This shows some of the telescopes that are involved in that, where they're located worldwide. When we participate in this network, the sensitivity of that network, now with the baselines giving you very high spatial resolution, the sensitivity of the network increases almost 5-fold when Arecibo participates in these observations. In fact, just last year we established the longest radio baseline ever established. We, in concert with a Soviet radio astronomy spacecraft, I forget the name of it. Maybe some of you know, Radio Astron, they call it. By doing simultaneous observations, we established a radio baseline of 220,000 kilometers. So this is a very important part of our future and something we're big contributors to. Our second Nobel Prize, I think, will be for the discovery of the first extrasolar planets. You may be aware that Alex Wolfstrom, who's now at Penn State, a former staff member at Arecibo Observatory, discovered originally 3 planets. Now they know it to be 4 planets surrounding a pulsar. Okay, one of the things we're great at is pulsar timing. So it's not a terribly interesting planetary system in the sense that it's probably pretty well cooked, but it was the first one, and a rather fundamental discovery of the planets actually are very common, which we all sort of suspected, but this sort of observation proves. So we did that. And of course, perhaps our most important research these days is near-Earth objects and image and getting their orbits exactly. This is an enhanced image of the asteroid Cleopatra 216. It is Arecibo research that's revealed that roughly half of near-Earth objects are actually doubles. And we also discovered the first triple asteroid system. In 2010, we participated with the Epoxy spacecraft mission in actually guiding that spacecraft to its close encounter with this comet. And these are the actual Arecibo images on the left. Not only were we able to range find it for the purposes of guiding the satellite there, but we actually were able to give them some idea of what the shape was when they got there and so forth. And those are the enhanced images on the right. Okay. We also do space weather research, if you will, or upper atmospheric research, which is actually my bag. And the second threat to humanity is our variable sun and how we respond to solar storms and so forth. So we're very much involved in that research today. Actually, we are a part of a chain of incoherent scatter radars that run from the magnetic equator in Jicamarca, Peru, through Arecibo, including Millstone Hill at what most of you know as Haystack Observatory, Sonderstrom, Greenland, and now 2 new radars that are here shown as a cartoon but are now actually in place, one in Poker Flat, Alaska, and the other in Resolute Bay, Canada. So this basically forms a magnetic meridional chain where you can chase the effects of a magnetic storm from the pole all the way to the equator along a single magnetic field line. But again, among those incoherent scatter radars, this is a log scale of the sensitivity of all those radars, and of course, Arecibo is an order of magnitude more sensitive than any other incoherent scatter radar in the world. So we're the most important instrument in that chain as well. This is an example real quickly of the kind of stuff we can do. This is a range of 1,000. At the upper parts of this scale, you probably can't see it, but the ordinate here runs from 500 to 1,500 kilometers above Arecibo. And this is then, as a function of local time on the abscissa, the density of the upper atmosphere of helium ions in the upper atmosphere in particular, which Arecibo is uniquely capable of measuring. So very much on the top side of the ionosphere, Arecibo is still sensitive. And by the way above LEO, common LEO orbits, we can still characterize the plasma environment there with very high sensitivity. I mentioned that we also have optical instruments. You can see the beam of our Rayleigh LiDAR here in the top right picture. We have 3 Fabry-Perot interferometers, which is mostly what I do, a spectrophotometer, a couple of photometers. We also do all-sky imaging.
Is that laser image enhanced at all?
In what's, no, this is just a short time exposure at night. Right now, we're only capable of operating them at night. Not operating them, but receiving the signal and digging it out from the day glow, if you will. But they operate at night, okay? And then I mentioned the different kinds of LiDARs that we have, a resonant LiDAR and Doppler LiDARs, and we also have 2 dye lasers, mostly for diagnostics. Most people think Arecibo only does radio science. We also do optics. Okay, these are pictures of, or data really over the course of a year of the density of potassium in the middle atmosphere, which we do with potassium resonance. This region of the atmosphere, by the way, around 90 kilometers, is really unapproachable by satellite, has traditionally been unapproachable by ground-based observation. You can't get balloons there. You can shoot a rocket through it for very brief, information. So my field has called this the ignorosphere, the part of the atmosphere we can't measure, except Arecibo can with these LiDARs, and it's a whole new opportunity at Arecibo. Okay, that's our history. Real quick, this is just our press releases in the last year. We detected what the headline said was the coolest radio star. This is work by that same fellow who had originally discovered the extrasolar planets. Basically, what we're able to measure at radio frequencies now are magnetospheres of brown dwarfs, which begins to open up a whole new way to look for extrasolar planets by looking for magnetospheric radio emissions. And so that's the importance of that study. I mentioned that we established the longest radio baseline with the Radio Astron satellite of the Soviets, or rather the Russians. We also found an asteroid that turned out to be twice as large as the optical people believed, which, is again waving the flag a little bit, but shows that Arecibo can actually get it right. Once we know where the asteroid is, we can tell you its dimensions very accurately, how it's rotating, and what its size is, and so forth, far better than the optical people can do. NASA spacecraft in November 29th, that's when the news story was published, actually confirmed the presence of water ice on the planet Mercury at the poles, which is something that our scientists had actually predicted more than a decade earlier by radio reflectivity. So we're proud of that one too. We also detected a massive outburst in a neighbor galaxy that was 10 times greater than a supernova blast. It was basically the signature of a black hole that was burping, if you will, but it was in the process of its evolution and released this massive emission, which we're still studying today. We mapped the Milky Way with unprecedented resolution in the last few years, and this was published in 2013. We found the largest star-forming regions and hundreds of previously unknown star-forming regions in our own galaxy. And then our most recent press release was relative to a neutron star. This one I wanted to title the overweight neutron star, but our astronomers were a little bit too stuck, and this was the title we have. But basically what's interesting about that is it defies the theory of the formation of neutron stars and of black holes in general, in the sense that they should never be this massive. So the upshot is that whatever matter is involved in this 2 solar mass neutron star is at present a state of matter that physics can't theoretically describe. Okay, so, and by the way, this was also a binary system that also confirmed the general theory of relativity. So we're still really good at what we do. I'm going to skip these, a couple of other things that we did this year. We also are able now, for the first time, to publish the winds and temperatures in the Earth's atmosphere at low Earth orbit. And we publish these every morning after a night's observation, so we're just a very short step away from what amounts to a real-time weather station that can tell you the temperature and the wind speed and direction at 300 kilometers above your head in real time. So that'll be the next step, but there's a website with this information published every morning. This is the HF project that I referred to. I don't know how well you can see this, but in the bottom left, you can see these large poles. These are sticking up through our dish. So the look of the dish is going to change. Those are going to be twice as high. They're going to be 90 feet high, and they're going to have dipole antennas on the end. And what they do is transmit the HF radio waves, and they reflect off a giant subreflector that we're going to hang between the current platform and the dish. So it's a major engineering effort. You can see the mesh of that subreflector, and that I guess it's the second picture from the top on the left. It's just thin braided wire, but it'll be nearly 200 feet in diameter hanging beneath the platform. And the energy from the dipole reflects off the subreflector, back off the main primary, and out to the ionosphere. And that's how we'll actually interact directly with the ionosphere. The picture on the bottom right is the actual dipole assembly being built, the cooling systems at the top, which is massive, and the 7 transmitters that will be ganged together to do this are shown on the second row on the right as well. So it's a very big project. If anybody tells you that Arecibo is finished, you can refer to this. We're pushing ahead in a big way. Okay, and finally to the education and the future. I like this picture, by the way. This is actually a son of one of our staff members speaking to some of the kids on the platform that come for visits every day. This is a picture of the visitor center. It's the neatest architecture on site. It was built by the Angel Ramos Foundation Visitor Center in 1997. At least half the money came from them. They also built another building called the Learning Center, and the other half of the money to build those facilities came from private donation. You know, it occurs to me, if you look in the background of this picture, you see one of the towers over which the suspension cables to the telescope are, and I think I need to paint that tower as well.
Do you have short courses there? One thing we do that we'll probably do is a tour.
Mm-hmm.
We're going to have ISP 2016 in Puerto Rico. But actually, it'd be nice if we had, like, people could actually sign up for a workshop where they could take like a half-day course or a full-day course.
We can.
Get a certificate.
We would be very excited to participate in that, as you'll see now as I go through some of these programs we have. I mean, this is the new Arecibo Observatory where we really want to participate in programs of that nature. Thank you. There was a study done by the American Astronomical Society in concert with the so-called decadal survey for astronomy around the U.S. It was part of that package. It was commissioned for delivery in 2010, and it was delivered in 2010. Maybe some of you are familiar with that. That study, just some of the bare bones of it, said that there were about 2,800 permanent positions in astronomy in the United States. Of those, from the period of 1988 to 2009, the participation by minorities, and by that they specifically meant blacks and Hispanics, was on the level of 2 to 4% through that entire period, even though during that period, which is already a ridiculously low number, but during that period, the same population in the United States collectively grew from 20.9% to 27%. So in fact, you can make the argument that that representation is regressing. While the population grows, the participation in astronomy remains static. Obviously, we're leaving a tremendous amount of talent, a tremendous amount of opportunity behind, and it's a population that needs to be served, as this study pointed out. Puerto Rico, on the other hand, generates about 30,000 degrees in engineering every year, okay? And yet, via 2010 census, it ranks last in the number of citizens percentage-wise with advanced degrees on the island among the 50 states. So basically, Puerto Rico suffers a brain drain, where they create a lot of technical expertise, but there's no jobs available on the island, so they go elsewhere. That's part of the story, okay? So, and Puerto Rico, by declaration, really strives to enhance its STEM education fluency and establish industries, spaceport on the island, that can actually use that homegrown talent. So my conclusion is where is my conclusion? Well, I'm rushing ahead. This is more to the, more fuel to the fire. That report that I referenced actually has a paragraph that says it's the critical role of national centers like Arecibo Observatory, the critical role we can play in reversing those trends. And I think it's obvious. Okay, and how they even told us how to do it. Create opportunities with intern programs, outreach programs, career mentorship through the undergraduate and graduate levels and postdoctoral years, and create opportunities nearby from the home institutions. That was what was recommended. There, it's the second paragraph here is my conclusion. I mean, the first paragraph says it is true that Arecibo Observatory has created 350 PhD theses in the 50 years it exists. That's a great track record. But we really ignored STEM education locally. These were astronomers who came to us and used our data, okay? So I conclude that by leveraging the icon that is Arecibo Observatory, we have an opportunity and we have a responsibility to enhance STEM education in Puerto Rico and throughout Latin America. This is something we simply have to do. So let me tell you about what we've done in the last year and a half. Okay, we do now activities on every level, from preschool through postdoc. Okay, so in terms of, and this is really unpopular with my staff, we've created a mascot that you see here in the top left picture for the preschoolers. And they go out to malls and local schools, daycare centers, wherever they have an opportunity, and show preschoolers, introduce them, if you will, to space physics. We also have started, and they're here today, the Saturday Academy. I believe this is the 4th term. That's a 16-week program that runs for 2 terms. It has 20 students, 10 in astronomy and 10 in atmospheric science each year. We also have high school vocational students. We had 4 of them active. We want to restart a program that I started in 2007 before the management transition, a program called the Inspiration for Science program, which is for K through 12 students, primarily about 3rd grade and up, okay, that brings, over the course of their K through 12 careers, will bring every student in Puerto Rico to Arecibo Observatory, which amounts to about 30,000 students a year. And there you see the beginning of that process. We actually have a bus company that repainted their bus as the Arecibo Space Tour. These kids come to the observatory by the busload, but it's not a formalized program yet. We're still working with the Arecibo Department of Education. A critical part of this program is 600 teachers that be trained in the program as well, and it becomes part of the curricula of the K through 12 program in Puerto Rico. So it's a big program that we're working on the K through 12 level.
Can I ask a question?
Yes.
Is that part of the core curriculum, or when it's inside the classroom, and did you tailor it to meet
That's the idea. You should appreciate that what we did 5 years ago was far more haphazard in the sense that we just said, bring the kids and bring them to Arecibo Observatory. They came prepared from their classes with questions that could be answered in our visitor center at the exhibit, so you would look for the answers, and that's about as far as it went. This time, the idea is to actually have a series of classes at each level that the 600 teachers are trained in and can deliver in their classrooms. So the idea is to integrate the experience at the observatory as just one part of a broader STEM push within the classroom.
We want to do curricular alignment with this type of teacher training workshops where the teacher themselves can align with their lesson plans according to the topics of the workshops they give. So the whole time that you have not only that teacher component, but something that kids can do at home and in their community.
Okay, so what you see here otherwise are some of the pictures of the Saturday Academy and some of our other activities on the high school level in principle. On the undergraduate level, we've had for 30 years and have again this year the Research Experience for Undergraduates program at the observatory that usually involves about 10 students each year, although we also cherry pick now 2 or 3 from the island to participate as well, so our numbers are usually closer to 12 to 13. Well, it's actually a separate grant, but it's the same program. NSF Astronomy funds that, and NSF Atmospheric Science.
And so they also have the RET.
Yes. Yes. You know what? We have one available this year, and I don't know if it's filled. We only had 2 applications, which is our fault. We should talk. Part of this is an RET program that asks that we bring 1 to 2 each year of this program to the observatory for a research experience too. Previously, under Cornell, we were criticized because those teachers, we ended up putting them in the visitor center, and they then interacted with the public, which was not the idea. They should be involved in research as well. So, okay? Yes? A real opportunity for us directly is to be involved in the CubeSat development. We have electronic expertise to do that. I have a CubeSat. We have a former staff member who is on 3 different CubeSat teams. It's definitely a direction Arecibo Observatory should go. I earlier showed a picture in the VLBI slide of a new 12-meter telescope we have. In the very short term, I mean to make that a satellite downlink station. So in terms of those kinds of space activities, it's a low-hanging fruit for Arecibo Observatory. And if you have ideas, I wish you would use Arecibo Observatory as leverage to get some of these things done, because it would be to our benefit and yours both. You know, we have the expertise, we have the instrumentation. What we don't have right now is that kind of expertise. I mean, in terms of actually doing the science programs. Also on the undergraduate level, we have interns now active on site that we have an arrangement at no cost to us that brings us, for each of 10 participants, 160 hours of labor on site. So they're now integrated into our electronics program, into our IT programs, as well as our structural engineering and mechanical engineering programs. So it's something we're currently doing. We have exactly the same relationship with National University in Arecibo Observatory, and we want to expand that on the island. I'm developing a study abroad program wherein we actually teach a study abroad program and bring students from various colleges in the mainland or elsewhere to study abroad for a semester, get a class in space physics, get a class in astronomy. These have actually been accredited, taught by my staff. Hope to launch that this fall, actually. The other courses in that are, of course, language, and we can either do scuba diving or culture. So it's a kind of a neat undergraduate experience. We think will be so oversubscribed that we won't be able to support it all. On the graduate level, you know, there's no degree granting program in Puerto Rico, which is something we want to develop. And so we are currently involved in a very large CREST proposal that teams us with the so-called nanograph community, which is pulsar timers. who are about the business of establishing, shown here on the bottom right, an array of millisecond pulsars that can serve as a timing chain that will actually allow us to detect gravitational waves. This was the second highest ranked research activity in all of astronomy in the US, again by the Decadal Survey and by the so-called NSF Portfolio Review. So this is something we do really well. We aim to form a center of this at Arecibo Observatory, and through that center, establish the first degree granting astronomy program on the island at Universidad Metropolitana. That won't happen overnight. It's a 5-year program, perhaps, but we're really excited about it. By the way, I think that'll be our 3rd Nobel Prize. In the meantime, because we can't get this PhD program off the ground immediately, we also have association with the University of Granada in Spain through the Spanish Research Council, where we intend to send about 5 candidates each semester who will get their academic training at Granada, but do their research at Arecibo Observatory and get PhDs immediately through that relationship. And that's all set up with the University of Granada, and we hope to get that going soon. So those are programs from top to bottom. I'm going to end real quickly now. We do all kinds of other public outreach now, and here's a whole list of them. The Alfalfa Workshop, for example, is a bunch of undergraduate students who actually do H1 radio astronomy and mapping galaxies. Planets and Stellar Remnants Workshop was hosted by Alex Wolfram at Penn State, and so forth. It's not just astronomy that we host, but we host now conventions of all sorts. You see a Hot Quarks group came to us for an all-day tour. CTEL, which is International Radio Spectrum Communications Group, came to us, and so on and so forth. This is something we actively try to do these all the time. So if people want to come to us and organize meetings on site and tour our site, the entire scientific community and beyond is welcome to do that. Okay? This is my final slide. We may be at middle age, but we have greater things ahead of us in the future. I hope I've convinced you we have greater things scientifically, but this educational push is central to our future. And this is my goal, is that we want to foster an environment that's responsive to our user community. We are still a service site. We're in your service, okay? And that's service in science and education, economic development, and that makes us part of Puerto Rico, not Puerto Rico part of us, and we think that's very important to our future as well. So I'll end it there. Thank you. Questions? Yeah.
What is the name of the LGM on the side of the bus?
The question is, what is the name of the LGM? Right, I'm sorry. The question was, what was the name of the LGM on the bus? I don't know what an LGM is. Oh, we're having a competition among the local schools. He doesn't have a name today, or she doesn't have a name today. I had a name that was completely rejected. I called him the Aricibalian, but didn't fly. Absolutely rejected.
Just a minor technical question. Why is the main dish spherical and not parabolic?
Hard to build a parabolic dish. It's hard to get that form right. The Chinese dish will be essentially, if you will, rubber parabolic, and they'll point by distorting the dish, which is one of the reasons it's unlikely they'll be able to use the entire aperture. It's really an interesting engineering design, but it was difficult to do in 1963. And by the way, for ionospheric work, wasn't necessary to focus very well. Yeah, that's how it's done. But you know, today with phased array technology and actually reforming the image in software is a real bright part of our future as well, and might allow us to go to higher frequencies yet. So you can take out the aberrations essentially by correcting in software with a phased array. Yes? Well, there are a couple of different millimeter telescopes, as you're aware, that are being built. But in terms of this frequency, there are no current plans except for mine. Yeah.
If someone were to say try to from the moon send a data package to Arecibo, would it be able to?
Oh yeah, we do moon bounces all the time. In fact, there's a legend that I can't confirm that one of the original reasons that ARPA, now DARPA, funded Arecibo was to intercept then Soviet radio emissions via moon bounce. But we do this as a ham radio show periodically to stay in touch with that community. So we're really good at moon bounces. We're really sensitive.
Is it feasible to modify the radar signal to detect latitude for ground penetrating radar on the moon?
I'm not expert enough to answer your question, but I can tell you that John Harmon, a former staff member of ours that just left during the management transition, retired, was actually looking subsurface on Mars as much as 2 meters and seeing the remnants of flows, be they water or be they lava on Mars as his final research effort. So our radar penetrates some distance beneath the surface of Mars as it is. I don't know if he's looking at a frequency slightly higher or lower than center or the detail of that, but we have some bandwidth in the S band and at 430, and I should also say at 46 megahertz, that we can probably make some contribution there, but I'd have to eschew to an expert to see if those frequencies were adequate. Okay?
I was wondering what that thing was in that James Bond movie. We got that figured out, don't we? Well, guess what, folks? Thank you all for sticking with us to this final and wonderful session. It was really informative. The whole conference was informative. I thank you all for being here, for being our steadfast of the National Space Society and the International Space Development Conference. Guess what, folks? We're going to close this baby. Officially closed at this moment. Boom. Thank you. Huh? Oh, yes, next year in LA. Are there any more announcements? No, I don't think so.